our final keynote. No pressure on the final keynote speaker, of course. I hope you've thoroughly enjoyed yourselves. Have you enjoyed yourselves? Yes? I've been most impressed. I've not seen one of these events before. And to see, one, the community close up has been most impressive, and to actually see you all and see how you interact with one another has been absolutely awesome. I didn't know this subculture existed, and oh my word. Okay, so we've got a marvelous keynote speaker for you. She's come all the way from London, which, as you know, I like people to come from exotic places, so I'm disappointed by this. She works for Cloudflare. She's a senior software engineer at Cloudflare. London Eye, I think she said she's traveled from, so there you go. Some of you out there will know where London Eye is. And she's talking about using Go to scale audit logging at Cloudflare. So for the final time today, I'd like you to give a Gophercon UK 2024 warm welcome to Arti Phugat. Go, Arti.
Thank you for the warm welcome. Hi, everyone. Welcome to my presentation, final talk of Gophercon UK. I assume many of you have encountered some type of an incident before. What's the first thing you check during incident? It might be logs, metrics, or whether any new code deployed to the production that could have caused this incident. In past, many companies have faced incident caused by some config changes. And that's where audit logs comes into picture. Today, I'm going to talk about how we use Go to scale audit logs at Cloudflare. We use Go to build and scale audit log. However, the same concepts can be applied to scale any application in distributed systems. Before I begin, a few words about me. I'm Arti Phugat, Senior System Engineer at Cloudflare. I began my career with C and C++. Then I wrote some code in Python. Later, I moved to functional programming and wrote significant amount of code in Erlang. And now I'm a Go developer. After working on these languages, one thing I can definitely say, Go is the easiest language to learn and work with. I love working on distributed systems and solving the challenges with them. Agenda for my today's talk, I will talk about what audit logs are and why they are important in an organization, how we built audit log at Cloudflare, the challenges we face when scaling audit log as throughput increased, identifying bottlenecks using various tools and techniques, solution to address those bottlenecks, and some key takeaways. Starting right at the beginning, just ensuring we all share a baseline context. What is Cloudflare? Cloudflare has a vision of building a better internet. To do this, we provide a global network to our customer that enables them to secure their websites, API, and internet application, protect their corporate networks, employees, and devices, write and deploy entire application that runs on the network edge. Cloudflare does this by providing products such as CDN, Zero Trust, Cloudflare Workers, WAN as a service, and many more. At Cloudflare, we are a big Go adopter, and we run at a massive scale. We started using Go in production since 2012, and it was chosen as the primary language for its high performance, excellent concurrency, extensive standard library support. These days, we have over 1,000 microservices and over 40 different teams writing in Go, with Go code running in all our data center around the world. Some of our application process millions of requests per second. At this scale, it's important to keep services independent and as decoupled as possible. For this, we rely on an event-driven architecture. So what are audit logs? Audit logs are definitely not service-level logs. An audit log is a log entry that contains details about action or changes that have happened in the system. Audit log contains the necessary information to reconstruct exactly what happened and what the nature of the change was. Who initiated an action in the system? This will allow us to understand who was behind the change. What was changed? What was the target of the change? When the change has place and when it was registered in the system. Where the change was initiated, is it using API, UI, or something else? And finally, how was the target changed? What's the value of the target now? This is a sample audit log. Here it's easy to determine who made the change, on which resource the change was made, time of the change, and some other details too. So you can see I updated the notification policy resource on 29th April via UI. The new value for the resource is reflected in the audit log. Additionally, an audit log ID has been generated for my action of updating target resource. So why audit logs are important in modern applications? For security purposes, to keep track of who made a change to some important settings in the organization. Was this person authorized to make these changes? For debugging and troubleshooting purpose, to keep track of what was changed and how. This could be useful to revert a change that leads to some issues or incident. Audit logs are critical for proving compliance with common regulator. And finally, for analysis purpose, how often changes are being made. We have discussed why audit logs are necessary. Let's talk about audit log at Cloudflare. This is the simplest diagram depicting different components involved in creating an audit log. When a request reaches API gateway, a call to upstream is triggered. Once the response is received from this service, the audit log pipeline is initiated. API gateway produces the HTTP request data as message to Kafka, an open source distributed event streaming platform. We'll talk more about Kafka in next slides. Audit log service running in Kubernetes consumes a message from Kafka. The service transforms the request into an audit log and interacts with internal service to enrich the audit log with required fields. After transformation and enrichment, audit log is stored in the database. Now, what is Kafka? It's an open source distributed event streaming platform useful for data processing. It has few concepts. Kafka messages are organized into topics, and each topic has a name that is unique across entire Kafka cluster. Producers are responsible for publishing messages to topics. Consumers read the message from Kafka by subscribing to and consuming data from topics. Topics are further broken down into partition, and each message within a partition gets an incremental ID called offset. Partitions are used to guarantee ordering of messages. To keep track of the progress, consumers use offsets. Think of these like bookmark. They are auto-incrementing integer. They act as a unique identifier representing the position of a record for the consumer. At Cloudflare, we deploy our application that work with Kafka on Kubernetes. We run both of these on bare metal, along with other systems like database. For those who are not familiar, Kubernetes is an open source platform for managing containerized workload, also written in Go. In Kubernetes, deployments are used to manage replica sets, which maintain a collection of replica pods. We run our application container inside Kubernetes pod. And pod are the smallest deployable unit of computing that you can create and manage in Kubernetes. What were the challenges we encountered while scaling audit log? We did a proof of concept to create audit log for a single Cloudflare product, and it worked well. However, challenges emerged once we scaled it across all Cloudflare products. The first challenge we faced was throughput. Throughput is the number of messages processed in a specific period. Production rate is the number of messages produced by Kafka producer in a specific period. Our initial throughput was approximately 30 to 35 messages per second when we were creating audit log for a single Cloudflare product. Consumption rate is the number of messages consumed by Kafka consumer in a specific period. We successfully consumed all the messages and generated audit logs accordingly. As depicted in graph, we managed to keep up with the production rate. However, when we enabled audit logging for all Cloudflare products, our throughput has now increased to approximately 2,500 to 3,000 messages per second. Now let's look at the consumption rate. While we were able to consume these messages, we struggled to keep up with the production rate. We were only able to consume approximately 450 to 600 messages per second. How about communication between services? We use Kafka for asynchronous communication between our services. Latency is not a concern for us since we were still in our SLO limit of 10 minutes to create audit log from the time user action was taken. For those who are not familiar, SLO stands for Service Level Objective. It's a key performance indicator that defines the level of service a provider agrees to offer to its customer. It's an indicator about specific metrics such as uptime, response time, throughput, or error rate, etc. What were the bottlenecks in the system and how we identify them? We use metrics to identify the bottleneck and utilize Grafana to visualize the metrics in Grafana dashboard. Metrics are used to measure the performance, productivity, consumption, and many other software properties over time. Offset lag is the difference between latest offset available in Kafka topic partition and the offset consumer group has consumed. The consumer lag refers to the delay between production and consumption of messages in Kafka. In this graph, you can clearly see the consumption lag is continuously building. Next, we use profiling. Many speakers talked about profiling in their talks today and yesterday. Profiling is useful for identifying expensive or frequently called section of code. Profiling data can be collected via HTTP endpoint. Preprof tool can be used to visualize and filter the top code paths. Go have several built-in profiles, and the one we find useful are these. CPU profiling helps identify the function that consumes the most CPU time during program execution. Memory profiling helps identifying memory allocation patterns and potential memory leaks in a Go program. Go routine profiling provides insight into the concurrency behavior of a Go program by identifying the number of Go routines created and their states. Blocking profile helps identifying the blocking operation in a Go program, such as channel operation, mutex locks, which may cause deadlock and affect system performance. We use profiling to determine which operation was taking the most amount of time in our application. Since our application runs in Kubernetes, we use port forwarding to access the port locally. The default port for profiling is 6060, but this can be customized. Next, we use curl to collect and download the profile output. In our case, we captured the 30-second CPU profile, since we were interested in the functions that consume the most CPU time. And finally, visualize the result using Go preprof tool. To view memory profile, use heap keyword after prof, and for block profile, use block keyword after prof. Similarly for other types of profile. Now let's look at the results. Here's what the preprof output look like. We transform the HTTP request into audit logs, which involve mapping to a particular API from the API schema, converting the API data to an auditable action, and enriching it by making internal service calls. We found that the request transformation took more than 5 seconds, and transformer method is where our system bottleneck lies. Some of you might have seen the flame graphs in presentation given by other speakers. Flame graphs are a visualization of hierarchical data created to visualize the most frequent code paths to be identified quickly and accurately. X-axis is alphabetically ordered stack profile, and Y-axis measures the depth of call stack. To generate flame graph, you can just go to View and click on Flame Graph. As simple as that. You can click on individual rows to know the CPU time for each method. Next, how about database insertion? We implemented metrics into our code base to track database latency and utilize Grafana to visualize these metrics in a histogram. Histogram is suitable for aggregated measures such as request duration, response sizes, etc. It appears that for most requests, insert queries were taking longer than 1 second when we were inserting rows individually. Definitely, database was another bottleneck that could be improved. We also use histogram to measure latency for calls to our internal service, Kafka message consumption. For most requests, calls to our internal service took 200 milliseconds. However, for some requests, it took more than 1 second, and in some cases, even 5 seconds. So internal services was another bottleneck, though not the major one. In our system, we were unable to consume messages at production rate. And the bottlenecks are request transformation was taking a lot of time, slow response from the downstream service during transformation, and slow insertion of data in the database. We have identified the bottleneck. Let's discuss how we solve them. How about horizontal scaling? Can we horizontally scale the system? Running a single instance of an application is just not sufficient. We run multiple instances of our audit log service to solve the scalability issue. In Kubernetes, we can run multiple replicas of a service by creating multiple pods. We run multiple instances of our audit log service across different regions to make it highly available and to reduce the overall latency. This allows us to run multiple Kafka consumer. I will talk more about this in next slides. Perform request transformation in parallel in separate pods, and make parallel calls to our downstream service. How to horizontally scale Kafka consumer? Use consumer group instead of a single consumer. A consumer group is a group of consumers that shares the same group ID in order to cooperate and consume messages from a set of topics. Consumer group allow you to distribute the processing of messages among multiple consumers, making it possible to scale out your processing capacity as needed. In Kafka, topics are split into partitions, allow messages to be consumed in parallel by separate pods. Each consumer in a group is assigned a partition and read from mutually exclusive partition. We created multiple consumers by running multiple instances of our application pod, as mentioned in previous slide, to consume messages from Kafka topic parallelly. We tried keeping the number of consumers equal to number of partition. However, we found that one-to-one mapping between pod to partition is not necessarily most performant. In cases where there are less replicas than partition, a single pod can consume from multiple partitions in separate Go routine. Also, it's important not to have more consumer in a group than you have partition. The extra consumer will sit idle since all the partitions are taken, and this is a waste of memory. In our case, to increase the throughput, we increased the number of partitions from 3 to 16 and created 4 application pods. This way, a single pod can consume from multiple partitions in separate Go routine. We used Sarama library for Kafka producer and consumer and created our own wrapper on it. To run as a consumer group, you first need to create new Sarama configuration. Then we implemented a consumer group handler interface. This interface has 3 methods: setup, consume clean, and cleanup. You need to implement these methods to handle initialization, processing, and cleanup of consuming messages from Kafka. Create a consumer group using new consumer group method. Pass which brokers you want to connect to, group ID, and consumer group config. Create an instance of your create an instance of your consumer group handler implementation. And lastly, start consuming from the topic. Sarama spins multiple consumers inside the consume function for each partition being consumed by separate Go routines in a pod. After scaling Kafka horizontally, how to further improve Kafka consumer performance? How about batch consumption? Batch consumption in Kafka allows consumer to fetch a batch of messages at a time instead of processing them one by one. We consume multiple messages in a batch from Kafka topics rather than fetching them sequentially. This can be achieved by setting batch size and flush interval. Batch size refers to amount of data that a consumer will consume before processing the messages. In our case, we set the batch size to 500. Flush interval refers to how often consumer should force a flush and process messages. And in our case, we set the flush interval to 5 seconds. Now let's see some code for batch consumption. As I have mentioned previously, we use Sarama library for Kafka producer and consumer. We created our own wrapper over consumer to support batch processing. First, you need to read the message from the channel, append the message to the buffer if the size is less than the batch size, and return nil when rebalance happened, which means context was done, and that will close the consumer. Messages are processed when either number of messages consumed is equal to batch size, means batch is full, Or flush interval expired, means consumer will process the batch of messages regardless of whether batch size limit has been reached or not. When a new consumer joins a consumer group or an existing consumer leaves, Kafka triggers a rebalancing process to redistribute the load. During this process, consumer stops consuming the data and partition is assigned to a new consumer. Therefore, it's important to handle rebalancing quickly and efficiently to increase the overall throughput. For this, we configured session timeout and heartbeat interval. Session timeout is used by consumer group leader to understand if the consumer is healthy or not. If processing takes longer than this timeout, this could result consumer claim lost. And in our case, we set the session timeout to 20 seconds, and the default value is 10 seconds. Heartbeat interval is used by consumer to send heartbeats to the consumer group leader that is alive. The value must be set lower than the session timeout, but typically should not be set no higher than the 1/3 of that value. And in our case, we set it to 6 seconds. Let's talk about how we improve the process for converting HTTP requests to an audit log. Go have rich support for concurrency using Go routines and channel. Go routine is a function that is capable of running concurrently with other functions. To create your own Go routine, you can simply use Go keyword as prefix to the function or method as shown in the image. Go routines are cheaper than thread and are different from OS thread. Go routines are stored in stack, and the size of the stack can grow and shrink according to the requirement of the program. But in thread, the size of the stack is fixed. In the example shown, we are calling display function as a normal function call and also creating it as a Go routine. Now, what are channels? Channels are a Go construct through which you can send and receive values. They provide a way for two Go routines to communicate with one another and synchronize their execution. Think of them as pipes that connect concurrent Go routines. And one of the Go prob mentions, don't communicate by sharing memory, share memory by communicating. On the left-hand side image, you can see how to create channels, send and receive values in a channel. And don't forget to close the channel to avoid memory leaks. We were transforming individual requests into audit log, which involves mapping to a particular API from the API schema using regex parsing, converting the API data to an auditable action, and making calls to our internal service for enriching audit log. Instead of doing this sequentially, we utilize Go routines for concurrent execution and use channels to pass the information between Go routines. This enables parallel processing of multiple requests. Now let's see how the new pre-prof output after using Go routines and channel. By processing messages in a batch, each batch now takes 3 seconds to transform, marking a decrease from the previous 5-second duration. To enrich the audit log with required information, we were making calls to our internal services, which was taking some time and adding network latency. Though it was not a major bottleneck, however, we wanted to reduce our dependence on internal service. To improve system performance and to reduce the latency, we cache the response from the downstream service in Redis. We use read-through cache, initially checking if the response is in the cache or not. And if it is not found in the cache, we call the downstream service and store the result in the cache. Since the data is static, we are not too concerned about cache invalidation. This graph depicts the latency for calls to internal service, including caching time. And there is a significant drop. Finally, how to improve database latency? Any guesses? How about batch insertion in database? We utilize a horizontally scalable database with a multi-master setup. To reduce the latency, we aggregated messages in a batch into a single query to store audit log into the database, rather than executing them individually. After doing batch insertion, latency is now dropped significantly. Something to take away from today's talk. We are at the last slide. Find the throughput and latency for your service and its dependent service. You can use metrics like counter and histogram for this. Use profiling to find the slowest component in the system. I think most people have talked about profiling in this GopherCon, so definitely use profiling. Run multiple instances of your service to scale it horizontally. Kafka can be scaled horizontally by increasing the number of partition and consume messages in a batch. Use consumer group instead of a single consumer. Go concurrency model is great for building decoupled component that runs in parallel using Go routines and channel, and batch queries while inserting into the database. Thank you all for listening to my talk. I hope you have learned something new from my talk today. Please check out Cloudflare API docs if you like to use Audit Log API. Thank you.